So today we're going to be talking about experiment 5, which is gas chromatography. Gas chromatography is an analytical technique, just like you learned about thin layer chromatography a few labs ago. This too is a way of separating components of a mixture. However, gas chromatography allows us to analyze gases essentially. But fortunately for us, it also allows us to analyze volatile liquids. So anything that we can get to boil, basically, we can analyze by gas chromatography. And so volatile liquids work pretty well for this. We're going to go through the components, the basic components of a gas chromatograph, and talk about the data that we get and how we actually obtain that data. Your TA is going to actually show you how to use the GCs that are in our lab, so they'll spend some time with you talking about that. And in this lab, we're going to be analyzing those samples that you obtained last time during the distillation lab. Well, all gas chromatographs, whether you're talking about the simple GCs that we have in our teaching laboratories or very sophisticated research grade gas chromatographs, all have some components in common. The first component that they all have in common is something that will look kind of like this, which is a heated injection port. You got to have some way of actually physically getting your liquid sample into the gas chromatograph, and that's the heated injection port. We also have a carrier gas inlet that's located at the injection port, and that carrier gas is, in our case, it's helium, but it can also be nitrogen, is also another common carrier gas. So you have helium coming into the heated injection port. Your sample comes in here and gets vaporized into a gas. That then gets carried into a column, so a GC column. It's kind of like your TLC plate, if you will. It's got a solid support in it that's got a very viscous liquid associated with it that the gas can actually partition into. So again, we're dealing with partitions just like we were with thin layer chromatography, except this time it's between the liquid and the gas state. And so we got a very viscous liquid on this column that allows the gas to dissolve into it, and then of course that can reboil and come out, and it allows us to separate mixtures based on their boiling point, basically. This column is located within an oven, so it's a physical oven. It's got a heating element in it, and it keeps the column at a specific set temperature that allows all of our liquids basically to be above their boiling point. And as the separated liquids come out of the column, it goes into what's known as a TCD, or thermal conductivity detector. That allows us to get a signal into the computer that we can look at and interpret. And once the sample comes into the TCD, it comes out, and the carrier gas and the sample come out, the gas outlet out the side of the GC into the room. The amount of sample that we inject is typically a microliter or less, so the amount of sample that you can analyze is actually quite small, and so GC is a very sensitive technique, even with our simple GC systems that we have. The way that the thermal conductivity works is kind of set up as what's known as a Wheatstone bridge, shown here. These are resistors connected in a loop, if you will, kind of like a square loop. You have two resistors that are set in the sample, and they're actually located in the TCD. And as the sample comes through, it cools these resistors down and changes the resistance of them, and hence results in a response. So when you have no sample coming through, the values for all four resistors are equal, and so the computer registers 0 volts across these two legs, and so there's 0 volts of response. However, when the sample comes through, it actually cools these resistors down, changes their resistance, puts an imbalance in the Wheatstone bridge, and then that gets recorded as a voltage. And so the computer then can read the voltage across the Wheatstone bridge and give that to us as a signal. What you will see on the computer is something that looks like this. It's known as a chromatogram. You'll notice on the y-axis, this is known as the response, and then the response here is in millivolts. So you're actually registering the millivolts across the Wheatstone bridge. And on the x-axis, we have time, also known as retention time. Okay? And as your samples, the mixture or the components of your sample mixture are coming out, you will get a series of peaks. The top of the peak is known as the retention time. And that is a constant that you need to record in your notebook. In this particular case, notice that we have 2 peaks coming out, which means that we have at least 2 components in the sample mixture that we injected into the GC. I say at least because this can only give you the minimum number of components. It's possible that one peak could actually contain more than one component. But we know in this particular case we have at least 2 components. And this allows us to determine, based on retention time, what those components are if we have standards. So if we have, say, a pure organic molecule, we can inject it on there, find out what its retention time is, and then take our mixture and shoot it on and use retention times to identify components. But we can also calculate what the percent composition of our mixture is. So we have these 2 components, A and B, and we can figure out how much A and how much B is actually in our mixture using a little math. Now these peaks approximate a triangle, and so we can actually integrate the peak using a very simple equation. We know that the area of a triangle is equal to 1/2 the width times the height. And so knowing the width of the peak and knowing the height of the peak, we can actually calculate the area. And you'll recall from calculus, if you've had calculus, that an integral is nothing more than the area under the curve. And the area underneath this peak is proportional to the amount of that component. So if A is twice as large as B, then you know that there's twice as much A than there is B in the mixture. For our purposes, however, it's usually very difficult to figure out what this width is. So we rearrange the equation just a little bit, and we say that A is equal to the width at half height. Okay? And so what we will do is we will figure out what the height is, and then we will look at the width at half that height, and we will multiply those 2 things together to actually get the area. You need to know how to calculate the area for these, for quizzes and on the final exam. However, it's very convenient for all of us that the computer can actually do the integrations for us, and your TA will go through that. Basically, what you will do is you will select the peak using your mouse, and the computer software will actually give you a value for the integral. It can do that for you. But again, you need to know the equations here for any quizzes or final exam questions that may come up on those assignments. So again, we've gone over what GC is, the theory of how it works, but it is a very powerful analytical technique that's used by organic chemists and analytical chemists alike. And your TA is going to show you how to use the specific equipment that we have in our laboratory. You need to realize that there are going to be a lot of knobs and buttons on those machines, and they're set to a particular value. He will or she will go over that with you, but please don't alter those settings once you get into the lab, because you could mess up the analysis for people coming after you.